Hello, everyone. How y'all doing? Let's see, can everybody turn my video camera, share my screen. All right. All right, can everybody see my screen?
Yep.
Yes.
Yeah.
Okay. Hello, everyone. Let's see, we are finishing up week number 10 of the current semester. And we started talking about transactions. I'm sorry, indexing. Today we'll continue some of that discussion and finish up with discussing about transactions that will allow us to work concurrently with other folks that might be using the same database. Next week we'll discuss NoSQL. Mentioning the fact that relational databases are not the only types of databases. We spent most of our semester talking about relational models, relational databases, but there are certainly many other types of databases out there, of which we're going to be discussing just two of them, MongoDB and Firebase, which don't use SQL. Right? They're not relational, and they address a completely different set of problems. And we'll see where they're appropriate, where they're not, and chat about that. After that, we can keep discussing. There are a couple of other topics that we could cover, but I would like to change the focus a little bit towards the project. Make sure that you have everything you need to be successful in the project. There is an assignment for P1 now, which I'm going to cover today, which won't be due for a while. Won't be due till the mid-April. But I'd like to encourage you to get started with that. Right? I want to encourage you to join a group and start working on a design and implementation of the database. So that's P1. We'll discuss that today. Let's see. And right, and the idea would be that within 3 weeks, right, you'll have a project working by the end of April. Okay. Anyway, so that's the plan for the next couple of weeks. Any questions? There is a quiz ongoing today, quiz number 6. It is on object relational mapping. So pretty much what you worked on in assignment 7, where you were annotating classes to map to certain tables. You're annotating things to be auto increments. You're creating repositories, things like that. Nothing to do with accessing things through a browser or exposing things through a URL. None of that. But everything about setting up a table, also doing a query. So yeah, so make sure you go over those slides on ORM. So all the quizzes have been moved 1 week later, right? So today's quiz 6, and then quiz 7, quiz 8 coming next week. Quiz 6 doesn't show questions. Well, they should show questions now. I'm not sure. I think I took a look at all of them. Let me see. Make sure I'm looking. That's right. Quiz 6. Quiz 6. Let me just check, make sure. Quiz 6. I'm going to preview this really quick. Yeah, no, there are questions there. Oh. So if there are, I saw that some folks might have started the quiz too early. Maybe, yesterday, the day before, when there were no questions, and they might have submitted. I've given everybody who I saw that they had started the quiz beforehand too early. I give them everybody an extra attempt. So you should all be good for that. For the project, if my group has students from other sections, yeah, let's talk about that. Let's talk about the groups. Yeah, let's do that. Okay, so let's talk about groups. So I saw that some students had created some groups of their own, but everybody had not created any groups whatsoever. So I created a whole bunch of groups for everybody. I call them database design 1 through 50. So there's 50 students. I see that some students have already joined. So if you could, if you could see that some groups have no students. If one of your team members, if you could find a group that doesn't have any students, if they could join that group, in that way they will be claiming that group, and then they can let all the other team members say, hey, I was able to join, team number 48 or whatever. And then all the other team members can come in here and join the group number 48. If you have it is okay to have students from different sections work together. And the way we're going to be doing it is going to have students from different sections join their own group in their own sections. So say, group number 45 in section 3 and group number 49 in section 4. If they want to work together, that's okay. So choose one of them, right? Join both groups. And then at the end of the semester, there's going to be a form that everybody's going to fill out. And you'll say, what groups belong, who's in the same group, right? So group, and you'll answer, group number 45 in section 3 is together with group number 49 in section 4, right? And so that way we're going to reconcile all the work that everybody has been submitting. So as long as just one of the groups submits the work, right, we'll be able to keep track of who's who and who's going to get the final grade, right? So if group number 48 submits submits all the work and they get 100, then anybody who's associated with that group, well, will get the same grade, even at cross sections. Yeah, only one person can submit, to that one of the groups. Yes, and we'll do the reconciliation at the end of the semester. As long as we know, what groups are together, we'll be able to do the reconciliation and basically say, whatever grade that one group got, all the other team members in all the other related groups are going to get the same grade. Basically, that's what it is. All right, so if you could do that right away, that'd be great. Okay. Also, because I believe the assignment can only be seen if you join the group. Okay, so here's the first assignment of the project. It's called P1, and basically here you're going to design the database, right, and implement the database. And by implement, I mean create tables, right? Create tables, associations, foreign keys, primary keys, all the fields, all the data types, and populate, some meaningful data, right? Some dummy data for now. It could be just sample data. So do the design, implement the relational model, right? And then export the UML. The design has to be in UML, and upload, as a deliverable, upload a PDF document with the UML diagram. And for the database, implement it using MySQL or Mongo if you're doing a non-relational database, and then export the database. Export the database. You'll the database will dump all your tables, all the data, any stored procedures, any whatever. We'll put them in a directory, zip up the directory, and then submit the directory as a deliverable to these assignment. Okay. The design and the implementation can evolve over time, right? So this does not have to be the final version of the database. I mean, you're free to modify it. If you discover that you needed an additional table or other fields, you're totally okay with designing, redesigning it and make any changes you want. So this design is a prototype, and this submission is mostly for you, as a milestone. We're just gonna check for it just to see that you've done something, okay? And if we see that you've done a substantial effort at the design and the implementation of the database, you should expect to get full credit, right? But we're not going to go back and forth, giving you feedback and suggestions. For that, come to office hours and discuss it with your TA and whatnot, right? But this is mostly for you, and just to make sure that you are making progress towards the goal of finishing up your project. The only way you get less than 100 is that if we see you haven't submitted anything and you haven't done anything whatsoever. That's the only way that you could get less than 100 on this assignment. Okay, so if you just show that you've made any significant effort towards designing the database and populating some dummy data for a database that you want to implement for your project, then you should expect full credit. Now, the database that you design and you implement needs to meet the criteria. Notice there's a link here. You click on that link, it'll open up the requirements for the database. So the database has some minimum requirements. Okay. So there's the following requirements. So first of all, right, you have to provide a UML class diagram, which is described in the assignment, the P1 assignment. And that UML diagram needs to contain class names, properties, data types, relationships, cardinality, and you should reify your database with the intention of implementing a relational model. Okay, so make sure that you have if it's a many-to-many, you have a mapping table or class, or you have an association, and right, you have aggregations and compositions, and all that good stuff. Okay. Now your UML diagram needs to contain the following at a minimum. You should have at least one class or table class and table that represents some user, right? So you need a user data model that represents some kind of human being. And this could be whatever you want. It could be an actor, it could be a faculty, it could be a student, it could be a cook, right? It could be a it could be a sports fan. It could be some financial guru. Doesn't matter. You get to choose the topic, right? You get to choose. So I use the word domain instead of topic, but I use them interchangeably. So depending on the domain or the topic that you choose, right, there will be a type of user in that domain, in that topic. Okay. Now your user data model should have at least these 6 properties. So a user should have at least a first name, last name, username, password, email, and date of birth. Okay. Obviously you're free to add even more attributes. You also need to model domain objects. All right. So domain objects are objects or classes or tables, right, that are specific to the domain or the topic that you choose. And so if your topic is movies, then a movie is a valid domain object, or a theater, or movie ticket, right? Or movie review. Those would be all classes or objects that are specific to the domain or topic that you choose. If your topic is food, then you can have recipes, right? You can have sandwiches, you have ingredients, pasta, or whatever. Any of those objects would be relevant in the world of food, or in the topic or the domain of food. If your topic or domain is travel, then objects such as plane tickets or reservations or hotels or airlines, right? Those are all objects that inhabit the domain of travel. Okay, there's a question in the chat. It says, can we store a password hashing in user instead of a plain text password? Oh, that'd be awesome. You're not required to do that, but that'd be totally awesome. So the question is whether for password here, if this should be clear text or if it could be hashed. Right? If you know how to do hashing, then definitely you should do that. But it's not required. Okay, so so you need to have at least 2 domain objects. So one user, one type of user, and 2 domain objects, or 2 types of domain objects. Now those 2 domain objects need to be related to one another, right? So this is the domain, the objects, right? The data model. Now the relationship between the data. Okay, so you have to have at least one relationship between a user and a domain object, right? So it might be maybe like a user might be an actor, and a domain object might be a movie, right? So an actor is related to a movie. We can say that an actor can act in a movie. Okay, and that's a many-to-many relationship, right? One actor can act in many movies, and given a movie, you can have many actors. So that's a many-to-many relationship. Okay, so you have to have at least one relationship between a user and a domain object. That relationship could be whatever you want. It could be a one-to-many relationship. It could be a many-to-many relationship. Okay. You also need a relationship between 2 domain objects. Okay, so a domain object might be a theater and a movie, right? If you're in the movie world, right? So a theater and a movie is a valid object in the movie domain, right? And the relationship might be that a theater can be playing many movies, right? So if I give you the theater, you can tell me what movies are playing in that theater, right? Or if I ask you, and that's also many to many, right? Because that movie could be playing in many theaters. So I could ask you both ways. I could give you a theater, and you can give me all the movies that are playing in that theater. Or I can give you a movie, and you tell me what theaters is that movie playing in, right? So your user interface should allow this kind of query, to execute these kind of queries. Right? Okay, this one's optional, right? But I highly suggest that you practice it and play around with it. It's a user-to-user relationship. Wait, what? Okay, user-to-user relationship, meaning a user could be related to another user, right? They could be, they could be family, right? They could be a professional relationship, right? One could be somebody's boss, right? Or there could be a social networking relationship, right? Maybe I follow you and you follow me, right? So, or I review you, or I send you a message, okay? So any relationship between a user and user, again, it's optional, but I highly recommend that you practice it. Then a portable enumeration, right? Remember, these are classes that have values in them, right? They're not records. I mean, obviously they're records. They're implemented as records, but they're not meant as records, as in I update records and I insert and whatnot, right? They're usually read-only records, right? That have valid values for that other records contain. Like for instance, if you have a users table, that users table could have a field called roles. And that sorry, role. Yeah, so a role could be that the role, I'm a faculty, I'm a student, I'm a staff. So I could have, any number of roles, but the value for those roles can only be taken from a set of valid values, right? And the way you implement that in SQL is you have the enum keyword, right? But we saw that that's not portable because other relational databases don't have enum. So how do you implement a way that could be used across all databases, right? All vendors. And we saw implementation of that where we implement a table that has all the values, that has primary keys, those values, and then other records can reference the values in that database, right? We implemented that for the assignment. I think it was the topic for the blogs. Blogs could be space and cars, I think it was. Right. So yeah, do something like that. Right. So roles could be faculty, student, and staff. Right. A semester, right, could have different quarters, and the quarters can be fall, spring, summer 1, summer 2. Right. Movies can have a genre. Right. They can have a horror, comedy, drama, sci-fi. Right. So those are all examples of enumerated data types. Okay, so user interface. So for the user interface, so for every user data model and for every domain object data model, you should have at least 2 screens. Right? Very much like what we've given you in the assignment, I think assignment 8, right? So for every object, right, like a blog or a user or a course or whatever, we have one screen that allows you to list all the items, and then a separate screen that allows you to edit an individual record or create that record, right? So for instance, if your domain was students or education or something, and you had your user data model was users, and your domain objects were courses and sections, right? And there's a whole bunch of relationships here, right? We can have that a course can have many sections. So there's a one-to-many between course and section. Students and sections have a many-to-many relationship, right? So one student can be in many sections, and one section can have many students. Okay, so your user interface should support all this, right? So for instance, there should be a student list that, typically it would show what? It would show the list of all the students. At least that's how we were using it in DB8. But that same list could be used not necessarily to show all the students, but could also be shown to display the students for a given section. And somehow, maybe starting from the section, or maybe, if you go to section list, right, and you select the section, in the section editor, you could provide, you could provide a way to navigate to the students that are enrolled in that section, right? So I could see the students in that. So student list can display all the students, but it could also display the students within a given section, right? That I could navigate maybe from section editor. Okay. Student editor will allow me to edit a particular student or create a brand new student, but it also should allow me to create a new student. For editing, allow or navigate to sections for that student, right? So for maybe a link that says, oh, these are the sections for that student. Course lists, right, displays all the courses. Right, notice that courses don't belong to anybody. If we had departments here, then yes, we would be able to navigate from departments down to the courses, but we don't have departments. Okay, that's okay. Right, the requirement is only 2 domain objects, so these are okay, right? So courses display a list of courses, or the editor, right, displays a particular course for editing, or allows creating a new course. Oh, this is and navigate to sections for that course. Okay. Section list displays a list of all the sections or the sections of a student, sections a student is enrolled in, or the sections for a given course, right? Because you can go from a student, you can go to the list of sections for that student, or from the course, I can go to the sections for that course. So there's two ways of going here, right? I could, from a course, I can get the sections for that course, and from the student, I can get the sections for that student. And from the section editor, I can display a particular section for editing, or allows creating new sections, and navigate to students for that section. Okay. So yeah, I will be providing samples of how to do all this, right? And I'll be providing a sample code. I mean, we already did this, right? We already started giving you code for the database that we've been playing around with, right? So that you can have a user interface that you can navigate from users to blogs, blah, 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 and how to relate them. I'll be providing more and more. I'll be adding it to the repository that we've been playing around with. I'll probably put it in a separate branch so that you can take a look at that. It'll be the solution to the assignment 7 and 8 will be there. So you can use that as a starting point for your own purposes. Okay. All right, excellent. So that's that. Any questions? All right, if there are no questions, then let's finish off the material that we started on Tuesday. Let's see. I think we were talking about performance. Let's see. Okay. Okay, so we had talked about that depending on whether you chose to implement a unique index or a non-unique index, you could get vastly different performance, right, from using one or the other. Right? And we saw that you would get much more performance if your indices were on unique keys as opposed to non-unique keys, right? And so here we have creating an index on a primary key, which is unique, and here's creating an index on a foreign key, right, which is not unique, right? And we saw that whereas this primary key was referencing an individual record, this foreign key could be referencing thousands of records, right? And that has a huge performance hit, right, in the query. So we have to make sure that we decide whether we want it or not, because depending on how the data is partitioned, it could actually work against us as opposed to improving performance. It could lower performance. Right? We also looked at query here, where that we talked about that we have to identify whenever we're trying to optimize and improve performance, we have to first define what it is that we're trying to optimize, right? And at first, from an algorithmic point of view, right, we had started in saying that we want to optimize the number of comparisons that we can count how many times it takes us to look for something in an array or a collection of data. But it turns out that that's not what we're trying to improve on, right? We're trying to improve the times that we go out to the disk, right? Because the operation of reading from a file system is several orders of magnitude slower, right, than any lightning fast comparisons that we might do at the CPU level, right? So that's what we want to focus on optimizing, minimizing the times that we have to go out to the file system to read something, right, and bring it into memory. Okay, so having defined that, we took a couple of examples where, say we had a university that had 40,000 students, divided across multiple departments, 40 departments, and having an average of 1,000 students per department. If we decide on that a disk block can hold 10 students, to be able to read all the records, it would take us 40,000 students divided by 10, that's 4,000 reads. That's how many times we have to go out to the file system to do a full scan of the table, right? We do, we go out once, we bring in 10 records. Then we go again, we bring another 10 records, right? So it would take us 4,000 times, right, to go out to the file system to read in all 40,000 records. So that's the number to beat, 4,000 reads. Can we do better than 4,000 reads? So it turns out that, right, if we use indexing on the primary key, if we're looking for a particular individual in the students table, right, we know who they are, then we have the primary key. If we use a full scan, right, we don't use indices, we could get very unlucky, and we have to, maybe the user is way at the bottom, it's the very last record. So the worst case scenario, we have to read every single record looking for that user, for that student. And if we get really, really unlucky, it'll be the last one. So worst case scenario, we have to do 4,000 reads, right? Now, if you're using indexing, remember, we're using these trees where we can use your ID and then traverse do binary search through this binary tree, going left, right, left, right, left, right, left, right, and we can very quickly, go to the record of where the actual student is, right? And it might take us a couple of reads, right, to identify, a couple of jumps, to read in the tree, right, and then the tree can tell us where the record is, and then we have to jump to the record. So say it take us, 3 reads to identify where the record is. So that's compared to 4,000 reads, that's huge, right? That's 1,300 times faster, right? So definitely, when you're talking about individual records that you're retrieving, then that's definitely a huge performance boost, right? But we have to be careful that this is not always the case, right? We have to consider that if instead we're using a key, an index that is not unique, right? Where we might say, the query might say, don't look for an individual student, but find me all the students that are in a particular department. Well, now you're talking about 1,000 students, right? So now you're not talking about one individual query of retrieving a single user. Now you're talking about retrieving 1,000 students, right? Individual students, right? So you would end up doing 1,000 reads. Now, if you don't have the indices, you still have to do 4,000 reads, right? As you go, you find and you compare the major ID, right, and retrieve the 1,000 students using 4,000 reads. If instead you use the indices, you know where those 1,000 students are, right? You just have to use their ID to go into the tree and look up and find the record. So those would be, but they would be 1,000 individual reads to database, right, to the file system. So in that sense, when your index is not unique, right, your performance boost is not as dramatic. Now you're comparing 4,000 reads for doing the full scan versus 1,000 reads, right, to retrieve 1,000 individual records, right? So instead of being 1,300 times faster, now it's only 4 times faster. So it's not as dramatic, right? And in some cases, it actually could be worse, right? Where, if the numbers were slightly different, right, where, you still have the 40,000 students, but instead of spread out evenly across the university into 40 different departments, say you only had 8 departments, right? So that would mean that you would have, on average, you would have 5,000 students per department, right? 5 times 8, that's 40,000 students. So now, since each department has 5,000 students, in the same query, where we say, well, go find me students in department number 20, well, that's going to be about 5,000 students that are in department number 20. So and then retrieving those 5,000 students, those will be 5,000 individual reads, one student at a time. Okay. Well, but if a full scan of reading the entire table and retrieving the 5,000 students would take you just 4,000 reads, then why would you want to do 5,000 reads, right? Using the non-unique index, right? You would be doing more reads, more individual block reads, using the index than if you just do a full scan read, right? So in that sense, right, using the index, right, on this non-unique field, right, it's actually working against you, right? So again, we saw how we can check the time, right? The database can tell you how long a particular query is going, right? And we can use that to determine the performance of one query versus another query, right? And decide whether the index indeed is worth it or not. Okay, so in this case, right, if the data is organized this way, right, where you only have 8 departments, then having an index on that field makes no sense, right? So we would remove that index. Okay. Okay, so yeah, composite. Let's talk about composite indices. So up to this point, we've been creating an index on an individual field, right? But there's also the possibility of creating what are called composite indices, where you take multiple fields, right, and you create an index on both fields. And what the database does is that instead of using one of the values with a value for a field, right, to search through the tree, to do the comparison, what it does in composite indices is it takes the 2 values from both fields and it concatenates them, and then it uses the resulting concatenation to do the comparison, right? So that if you're searching for a particular car that has a specific model and year, right, it'll use, in a where clause, you might have where model is Toyota and year is 2021, whatever, right? The key would be the concatenation of the model and the year, and that you would use to the structure, the tree structure, the B tree structure would be, each node would be the concatenation of model and year, right? So that when you're finding something and you're doing binary search, you would traverse this tree with the concatenation of those 2 fields, as opposed to just one of them. Now you could create a model and year, concatenate it either starting with model and year, or you can switch them, right? It could be year model, right? And depending on your query, it could be very consequential, whether you chose to concatenate it one way or concatenate it the other way, right? Starting with one of the fields or the other field. So also that, the fields, the queries are going to drive your decision, right? To do the composite indices and what kind of, which order you're gonna take, which fields you're gonna concatenate. Okay, so let's take a look at some of these examples, right? Where here we chose to use create a composite key using model and year, and we could have chosen to either do the model first and then the year, or we might have chosen year and model, literally by swapping the order of these keys like that, right? Here we chose model concatenated with year, or it could have been year concatenated with model, either one, right? So which one to choose? Well, we have 2 choices. We chose model year or year model, and one would be the concatenation of starting with the model and then the year. The other would be instead the opposite, right? Starting with the year and then the model. And once we have all those concatenations, then we would create the tree, right? We create this B plus tree that allows us to implement binary search. Okay. And so it would be sorted only one way. Here it's sorted by model first, right, all the way through, whereas here it's sorted by year first. Okay. Now, if your queries have in their where clauses, right, if you have both fields, year and model, both fields by which you have the key, the index, then it doesn't matter whether you chose either model year or year model. It doesn't matter, right? The algorithm will take the values 2004 in Odyssey and will concatenate whatever it had created, this one or that one. In both cases, right, it'll very quickly traverse the tree, the binary search tree, either this way or that way. So either one works.
Hey,
doesn't
Professor,
matter. Yes.
you just cut out a bit. I'm sorry.
Oh, I did.
Yeah,
Let me.
but you've been really good so far.
Thank you. I did a speed test. I have 44 megabits now. It's not bad. Yeah, so I should be okay. All right, yeah, sorry about that. So I was saying, let me go back a little bit. So composite indices, right? Yeah. If your query is using both fields, right? Both fields that were used to create the indices, then it doesn't really matter which one you choose, whether the order was model year or year model, because the database is going to remember how you created the keys, right? And it will do the right thing. It'll concatenate either year model or model year before it goes into the data structure, the tree structure, looking for the left, right, left, right, left, right until it finds the leaf. Okay, so when you use both fields in the query in the where clause, it's inconsequential, how you declare this index, right? But if your where clause, right, in your where clause, if you only have one of the fields, if you have year equal 2004, then now the order does matter, right? It's because if you have year equal 2004, right, it'd be very convenient if the keys were ordered, right, alphabetically or numerically, right, by year, right, so that you can find 2004 first, right? You can follow the keys by the year. It would be completely useless to you if instead it would have been model year, right? Because the year now it's after the concatenation, right? So it doesn't help you that it's organized or sorted by model, because now it's the same thing as the year being random. It doesn't really matter. So if you're using one field in your where clause, then it does matter the order, right? Same thing if your query were only using the model, then the left-hand side is useful, right? That is model year and not year model. If you went with year model and your query was started with model, then it's this query, this ordering is useless to you, right? Right. So let me see, is there a question in the chat? Can we store password hashing in user instead of plain text? Somebody asked this before in the previous section. Does only one person? Yeah. I think, okay, somebody's asking if they can store the password in hashing instead of plain text. If you know how to do that, then yes, by all means, please store passwords in encrypted form. But it's not required, okay, for the user model. All right, so to index or not to index. So yeah, so we saw already, right, that not always index is by default going to help you, right? It might actually be worse. We get worse performance. So the question is, well, to index or not to index, right? That is the question. And so there are a couple of things that we need to consider. Not only performance, time based, how much time does it cost, right? Or any benefit, any decision needs to consider, right? What are the costs and what are the benefits, right? As somebody said at some point, there are no solutions, there are only compromises, right? You can only if you get a good thing one way, there's something that needs to be paid for that, right? No free lunch. So for instance, if you had a product database that was 8 gigabytes, and so you have to consider, well, do I index it, right? So the first index might be the same size, might resort the whole table using a particular, maybe the primary key or some field that is unique, right? And then any additional keys or any additional indices probably will be smaller, maybe a fraction of the original table, right? Because it'll have maybe just that field that you've indexed, and maybe the record identifier that allows you to go back to the original table, right? And each additional index will be, again, a fraction of the original, but it starts to add up, right? So a table that was originally 8 gigabytes, when it's indexed, in total, it might be more than double the original size, right? And somebody might say, well, who cares, right? I mean, data is cheap, right? Memory is cheap, right? So who cares? But not only are you talking about the amount of memory, but it's also the complexity that goes along with that, right? Of having now to maintain all these different versions of the database that might exist across the entire enterprise, right? Where not only is there the database that day-to-day folks are using that is in production, and you have thousands of users using that database, but that database typically has multiple copies for disaster recovery, making sure you can survive World War III, or the zombie apocalypse, and you probably also have multiple versions or copies for in your development environment, right, where developers might have a copy of the database, probably with obfuscated data, no credit card numbers, no real social security numbers, right, where no real names, right, so that developers can work and implement applications, right? And they might have multiple development environments, right, and each one with its own indexing and whatnot, right? And in their development process, probably they'll have initial copy for the QA folks, the quality assurance, for the user acceptance testing, that they deploy this every day so that the QA guys can go in and try to find errors in the functionality. They might have also another copy for performance testing, right, where they can bombard the application with a lot of denial of service attacks and all sorts of vulnerabilities that they're trying to identify every day, right? And there's going to be mirrors of these everywhere. So, I mean, you're talking about a fair amount of data and complexity of having to copy and move these things around. So an overall consideration, right, might determine whether you should index or not. This also, that performance is not necessarily free, right? If you improve the performance of retrieving data, right, you have to consider, if this is a mostly read table, then perhaps that's okay, right? Where you're going out to a table and you're doing a lot of individual queries, right, retrieving individual records. Then most often that's doing an index on that table, on that particular set of fields for a particular set of queries. Then definitely that might be a really good idea, right? But if your queries instead involve retrieving a lot of data, right, a lot of long list of records that are being retrieved, where very, very commonly are retrieving a quarter of the table, right, or 10 or 20 or 30% of the data is being retrieved constantly, then perhaps a full scan is just as good, right? That indices are probably not doing much good to you, right? Also, right, if that table has a lot of reading, a lot of, well, not only you have a lot of writing to the database, right, where you're inserting or you're updating constantly the data, right, then probably indices might work against you, right? Because we already saw that, right, when we were looking at the demo that we looked at on the last lecture, we had two tables that were identical, but one had indices and one didn't, and we saw that the one that didn't have indices was several orders of magnitude faster than the one that did have indices, right? So here's an example of that you have hundreds of thousands of records, and for the same amount of time that it takes us to do 100 inserts, right, with no indices, we see that every time we add an index, we see that performance drop, right, from 100 inserts with one index drops, significant amount, right? It drops, a 30%, 35% hit, by just adding that index. And when you add that second index, it drops almost 80%, right, the performance. And with the third index, it drops already, almost 90%. So every time you add an index, right, the insert speed just drops dramatically. So obviously those things are also have to take into account. What kind of operations are you using your database for, right? So you should not automatically just say, oh, well, index is going to solve everything. So you have to be careful. Okay. All right. Okay. So any questions about index? All right. So if no questions, let's move on to transactions. All right. So transactions. So transactions are going to deal with issues of allowing folks to collaborate or cooperate in a database, right? It's up to this point, we've been working with transactions with databases as if we were the only ones working with the database, right? And for the most part, yes, that's true, right? It's just being you, right, hitting your database, logging in as that one person and dealing with the database yourself. But in reality, when you deploy this in a production environment, it's most likely that you're going to have dozens, hundreds, thousands of people, hitting your database simultaneously. Okay, and so how is it that you reconcile folks that are trying to manipulate the database at the same time? Okay, here's an example where you have multiple processes, right, running simultaneously, are trying to determine whether this user has a specific age or not. Some of them are trying to read the data, some of them are trying to update the data, others are trying to remove the data, right? Or somebody is trying to insert records in there, right? So how do you reconcile everybody trying to manipulate the same piece of data, right? Imagine, right, you going out to make a reservation for a restaurant, and you look, tables are available, and or maybe buying a ticket to travel somewhere, and the UI displays that these following seats are available. Now, how do you reconcile the fact that you're probably not the only one looking at these seats, right? Probably you're looking at hundreds of other folks looking at the same seat. And so what is it? I mean, is it first come, first serve? Is it random? Is there a timer? What is it? How do you reconcile the fact that you might have multiple folks looking at the data, and that they might be looking at data that is stale, that's no longer valid, and that they're trying to make a decision based on information that is incorrect, right? So we need a mechanism, a way that we can somehow reconcile everybody's vote, right? And if we made a mistake, we need to have a mechanism for retracting or going back to a place in time where there was, the database was consistent. Okay, so we want to avoid inconsistency, but if we do run into inconsistency, we need to be able to backtrack and go back to a previous state of where the data was consistent. Okay, so transactions are going to deal with this challenge by introducing what are called isolation levels, or levels of isolation, right? Where yes, everybody's gonna, you have all these multi-threaded environments and multiple processes trying to interact with the database, but they should be able to behave as if they were the only ones interacting with the database. Okay, they shouldn't have to they shouldn't have to worry about others. Okay, the database should provide a mechanism where each one can be safe, and that they are guaranteed that they're not going to have some inconsistency in the database, right? We say that transactions allow us to create atomic units of work. Okay, and what we mean by that is that even though commands and individual select statements, individual updates and deletes and inserts, the database considers them to be unique or individual. Logically, for us, we might think of 3, 4, 5 different operations as being logically one, right? One single thing, one single operation. For us is one single atomic thing. For instance, if we are transferring money from one account to the other, and we think about that logically as one single thing, you transfer money between account 1 and account 2. But that actually is implemented as 2 different operations where one account is debited and the other one is credited, right? So it's actually 2 operations physically, but logically for us is one. It's a transfer, right? So the database allows us to group together, right, individual operations or individual transactions, right, as if they were logically one, right? Because if we didn't have, if we couldn't group together these 2 operations, then just imagine, right, the operation 1 occurs where we are transferring $100 from account 1 to account 2, and we were able to debit one account with $100. What if somehow, right, the system goes down and crashes and burns, and before we had a chance to deposit, right, or credit account number 2, then we would be losing $100 somewhere, right? The account here was debited $100, but we never got the chance to deposit in the other. So transactions allows us to group this together so that they both have to be successful to consider the whole thing successful. Okay, so transactions allows us to kind of make a mark, right, saying, hey, we're starting the transaction, and it ends when we are able to deposit. Okay, when we deposit, then we are going to lift the transaction. Okay, so if we have a flag saying that we were able to debit, but we were not able to deposit because we never reached the other end of the transaction, then we can always backtrack and say, okay, well, let's undo everything that happened in there, whatever it was. We don't know what happened, but we have a marker on where this transaction began, and we can roll back the entire database back to the initial state of before the fault or the failure happened. Okay, we can go back to a previous spawn state, right, of where the database was, back to a consistent state. Okay. So yeah, so so the book travel example that we mentioned earlier. So databases, transactions introduces things such as being able to recover from failures, right? That we can define reliable units of work, right? That either the whole thing occurs or none of it occurs, right? That we can recover, right? That it leaves the database in a consistent state and isolates the processes from each other, right? We say also that these in different words, right? We say that the transactions provide the ACID properties to a database, right? Databases that support transactions are said to support ACID properties, meaning they're atomic, right? Meaning that you're able to group together logical units of work, right? Whether they all occur or none of them occur, right? That they are introduce consistency. Transactions make sure the database stays in a consistent state, right? And if it can identify when some inconsistency occurs, so that we can go back to a version of database that was consistent. It provides a mechanism for multiple processes to isolate themselves so that they're not trampling on each other's work, and durable, right? That any changes that we make to the database, right, are going to be stay with us, right? From if we make the change today and we lose power, we guarantee that the next day the data will still be there, right? Any changes we make are permanent. So the way transactions are able to do this is by using many of the mechanisms that we introduced last time we met, right? We were able to start a transaction. We're able to either and any changes that we make in the database within the transaction are only temporary. Not until we commit those changes will the changes become permanent. Okay. Or we might even decide that we don't want those changes anymore and roll back the whole thing and just throw it away and go back to where the database was before we started the transaction. Okay. Now the question is, as a transaction is going on and we're making these changes, what kind of isolation do we have from other transactions or other processes that are doing the same thing? Do we see each other's changes or don't we see each other? We saw that on Tuesday when we looked at the demo. We saw that different transactions, different users would not be able to see each other's work, and we'll talk about that. Why is that? Okay, so so let's introduce some of the things that could go wrong, right? What are typical things that go wrong when you have multiple folks, right, trying to touch the database at the same time? And what we'll see first what could go wrong, and then we'll see how databases or transactions can deal with these issues, right, and make it better. Okay, so first of all, one of the things that could go wrong. So these are three very common categories of things that could go wrong. One of them is what is called a dirty read. And so a dirty read means that somebody might be making changes to a database. Perhaps they might have started a transaction, right? And they're changing values. They're changing somebody's age, changing somebody's salary, changing somebody from a department, whatever, right? It's updating, inserting. Now, the transaction hasn't completed yet. So meaning those changes that are in transit, right? They haven't yet settled. Okay. And if we allow others, right, outside of transaction to peek inside and take a look at that data, okay, if we allow them to read the data and take that data, read it into memory, and then they go off and do something with it, right, and they start making decisions based on that data, we have committed a dirty read. We have read data that we don't know yet if it has settled, if that is the final value of that data, because it hasn't yet committed, right? We saw that we weren't able to do that last time, right? On Tuesday, right? We saw that we weren't able to do that. But that's because the database had a default isolation level, which we'll see in a minute. Okay, but so in this scenario, there would be no isolation, right? Everybody could see everybody's temporary work, right? Nobody would wait for anybody to settle anything. Okay, this is isolation level called read uncommitted. It's called read uncommitted. Okay, that is the lowest isolation level, meaning no isolation whatsoever. Everybody can see whatever everybody else is doing, right, without waiting on each other. Okay, when that happens, when everybody can see everybody's work without waiting until things are committed, right, we can encounter this type of problem dirty reads, right? You're reading something that is dirty, it hasn't yet been settled. Okay. All right. So the next type of problem we might encounter is what is called a non-repeatable read. So a non-repeatable read occurs when your algorithm, when your code assumes that, you know, if they do a read from the database, so they read something, now they copy it into memory, and you write your logic as if you're the only one, right, who's going to read that information, that you're assuming that nobody's going to come in and change that, right? That no other process is going to come in and change that value for you. And so you make that assumption that you read the data, now you're doing something, you're making decisions, you're doing a whole bunch of things, and you go on in your algorithm as if you're the only user who's ever going to read that information, which is not true. Okay. So if your logic is based on assuming that the read is repeatable, meaning you're assuming that if you read it multiple times, you're always going to get the same value. You're assuming that, then you could be vulnerable for non-repeatable reads, meaning a read that if you read it again, you could not get the same value as before. Okay, so you have to be careful, right, about the way you write your logic, right, and you should be careful about the things you should expect on how the database is behaving. Okay, so yeah, so non-repeatable reads are, you know, errors where you might assume that you can read it multiple times and you're always going to get the same value, and it's just you. Okay, so that's one problem. The other problem is called phantom reads. So phantom reads is similar to non-repeatable reads. So non-repeatable reads applies to a single record, right, or a single field in a record, right? Whereas phantom reads applies to a whole set of records, right? Maybe a range of records, right? Where you do a query, right, and it comes back with a whole bunch of records, you know, 20 records, 100 records, whatever, right? And so you do the query and it comes back with 100 records, right? Now your logic, again, you could assume that once you read those 100 records, that's it. You're the only one who asked for those records, and you're assuming that somebody's not going to insert something else in the database or delete records, right? That would have affected your original query, right? That if you just had waited, you know, a millisecond later, instead of getting 100 records, you would have gotten 110 records, or maybe 90 records. Okay, that, you know, records are changing underneath, right? Somebody's inserting, somebody's deleting, right, or changing, updating some values that would have affected your original query. Okay, and so you go on and in your logic, you assume that those 100 records are the only 100 records, right? And you make you make decisions that are erroneous, assuming that those records are not going to change. Okay, and so you are susceptible to this type of problem, phantom reads. Okay, all right. So how can databases deal with this? Right. So databases can deal with this with what are called isolation levels. Right. Isolation levels, meaning you can configure the database, right, to allow certain things to happen or not. Okay. So it can go out. It has 4 levels. One of the levels is everything goes. The database is not doing anything, right? You know, anybody can read, anybody can write, doesn't matter. It's free go for everybody, right? So this is like, you know, we go out to Dunkin' Donut and you don't have to make a line, right? Everybody just goes to the counter, right? Starts shouting at the server what they want, right? And it's just a huge mess, right? And in some countries, you know, that's actually a very common thing to do. And right, and it's a free for all, right? And you know, obviously it's a mess, right? So that's one extreme. One extreme, everybody can do whatever they want, and it actually might be okay, right? Things might still work. Let's see, there's a question in the chat. It says, Is this similar to how GitHub works with the transaction commits and rollbacks? Yes, exactly. So, right, Git. So Git takes another approach. Git in other source controls like Visual Source Safe. In Visual Source Safe, they took the approach of what we're going to see a little later, serializable, where if you check out a file, right, you're the only owner of that file. Nobody else can. Everybody else can read that file, right? But nobody else can change it, but you, because you have it checked out. Okay. Whereas GitHub takes a different approach where multiple people can check it out, have their own copy. Okay. And what we'll do is that when you both commit and bring it in, it'll try to merge the changes, right? And if there are any conflicts, then you have to resolve those conflicts. Now, most of the times, hopefully, if you're careful, you can minimize those conflicts, right? Because most of the times, right, I'm working down at the bottom of this here, and when you do the merge, there's no conflict. The problem is that when we work on the same lines of code, and now there's a conflict, and there has to be a resolution. Okay, so what GitHub does is that it allows you to have read uncommitted. It allows you to have read uncommitted, but right then gives you all the tools for identifying what the conflicts are, right, and then using a human being to be able to pick and choose which version we want and do the merge. So we'll try to merge most of the code again, because in that case of source control, right, it relies on the fact that we use other ways of coordinating, right? That, hey, I'm going to be working in this class over here, or in this piece here, right? And usually then other people are not going to be working on the same type of feature, right? So we use planning, and we use Jira, and we use many other tools to make sure that there's no duplicity of work, right? If I'm working on a feature, well, I'm the only one working on that feature. So I should be the only one working on a set of files, right? And any merge conflict, we deal with them with doing incremental changes, right? Making sure that if somebody else is working on something similar, where we merge those changes into our, right, and make sure that we're always up to date, right? And we don't have like a huge merge conflict at the end. So anyway, so too much in Git. So yeah, so read uncommitted is the, everything goes, and it actually might be okay, right? It actually might work for you, right? So for instance, if a table is a mostly read table, right, with a table that has some static information, maybe just values, right? It's a value table, or right, or enumerated data type, right? A list of countries, right? A list of departments, and those tables are not changing very often. Maybe they change maybe once a year or something. Then there's no point in having any transaction isolation, right? Everybody should be okay to just read the data. You're just reading the data. So read uncommitted is just fine, right? Because it's not like you're going to be updating the name of the country multiple times, and there's going to be a conflict of other people changing the name of the country, right? So in that case, read uncommitted is just fine for that particular table. Okay. So if it's read mostly. But if you have a transactional table, right, where things are changing all the time, right, then you have to consider using things such as read committed, meaning I don't want to read anything that has not yet committed, right? And this is what we looked at on Tuesday. On Tuesday, this is the behavior that we saw, right, where we saw two users logging in and seeing that one transaction was making changes and the other user could not see those changes, right? Because this is the default behavior of databases. Most databases will start with this isolation level by default, where two different transactions, two different users can't see each other's uncommitted changes. Not until you commit, we'll be able to see those changes, right? So this is the default isolation level. You can go a little further, where you can ask the database to enforce repeatable reads, meaning that if somebody is reading or doing a select statement on a particular field or a particular record, right? Not until you commit will that. So what it does is that it acquires locks. If you do a select statement on a record, right, or set of records, well, no, only on a record, on a single record, right, you acquire a lock on that row, so that if other folks try to write to the same record, they will not be allowed to write to that record. They'll have to wait. Right? They'll put in a queue, right, and they have to wait until that, whoever is working with this record does the commit, and then the locks are released, right, and then anybody who was in line in the queue then can come in and then make updates. Okay, and then finally you have your serializable. Serializable is the other extreme, right? If read uncommitted is the chaos, everything goes extreme, right? Serializable is the other extreme, right? Everybody is in lock step, right? Everything happens in order, and so that now instead of just locking one row, right, I might lock a set of rows or maybe an entire table, right? And so now I don't allow to have multiple threads come in and start changing or modifying or reading the data simultaneously. Instead, everybody needs to get a ticket, right, and wait in line, to access the data, right? So obviously, each one of these levels is an increasingly demand on the database, right, to make sure that things happen in order, right, and which goes against the other goal that we have of being as concurrent and providing as much concurrency as possible, right? Because concurrency also gives us efficiency, right? So read uncommitted gives us the most efficiency, right, where most threads can run at the same time, but gives us also the most risk of inconsistency, as opposed to serializable gives us the most consistency, but gives us the least amount of performance, right, and concurrency. So again, there's no solution. There's only compromises, right? It depends where certain tables you want read committed, certain tables you want read uncommitted, some you want serializable. It depends, right? And you have to make those decisions case by case, right? So here's an example of each one of these problems, right? And how might they occur? So first of all, let's look at this one: read uncommitted data. Right. So read uncommitted data means that a transaction might be changing data, and another transaction comes in and can read that data. Okay. So for instance, assume two transactions. These could be two users logged in, two separate users, two threads through two processes logged in and interacting with the database simultaneously. So one of them is running an algorithm that is swapping two professors, right? You have Einstein, right, and you have Brando, okay, and you want to swap them, right? One is teaching drama, the other one is teaching physics, and now they want to try and teach each other's courses. And you want to swap them, okay? But swapping means that I need to unregister one of the professors, right, while I then register the other professor, okay, and then register this one over here, right? So I need to swap them. So, but meanwhile, while I'm changing and unregister one of the professors from one of the sections, at the same time I have another algorithm that's calculating the year-end bonuses, right? Because I want to give my faculty bonuses based on the number of sections that they teach. So what happens if transaction one is able to remove Einstein, and I have not yet put Brando, right, and give him a section over here? What if it runs right in the middle where I remove Einstein, right? And it calculates the number of sections. So T2 is reading data that has not yet settled, and it might make the wrong decision, right? And calculate that Einstein is actually teaching, one less course than we thought. So he's going to get a lower bonus at the end of the year. Okay, and we don't want that. Okay, so yeah, definitely this could be consequential, right? Of allowing folks to read things that have not yet settled, right? I'm not done yet, right? You cannot read things that are still in flight. Okay, so yeah, definitely consequential, allowing reading uncommitted data. Oh, how about this one? Repeatable reads, right? So my algorithm here is going to read data from the database. It's going to assume that that data is not going to change, right? That they're the only holders of the truth, but it actually is changing underneath. But their algorithm is written in such a way that they assume that they're the only ones holding the truth data. So for instance, you have a student that has $50 in their account, right? And that's what their parents deposit in there for them to buy food and whatnot, right? So what happens if you have the student goes in and they want to withdraw $10 from their $50 in the account? So as they're withdrawing, at the same time, their parents are depositing in that same account. They're depositing, $1,000. They deposit every month $1,000. And so T1 reads $50. So they read the $50 in the account, and then it makes the logic. Oh, how much do you want? $10? Okay, well, here it is. Here's $10. It dispenses the $10 in the ATM, and then it makes its calculation. Well, 50 minus 10, that's 40. So it basically would want to say, okay, well, I'm going to go back and tell the database to update so that its balance should be now 40. Okay, and that'd be okay if transaction 1 was the only one with access to those $50. But since you have T2 that is happening underneath, right? That happens after I read the $50. T1 reads $50. Transaction 2 comes in and deposits $1,000. So as far as T2 is concerned, there's $1,050 now in the bank. But here comes T1, having subtracted 50 minus 10, 40, it goes back and puts the $40 back in the database. You just lost $1,000. It's gone, right? Because your logic was based on false information. Okay. So again, very consequential. So here's another example. We're doing a phantom record, right? Phantom reads, okay, where you have a query. You have at the end of the year, the students have saved $100,000 from selling tickets and selling all sorts of events throughout the year. And at the end of the year, the department has an average 1,000 students, and they're trying to decide what to do with the money that they've gathered throughout the year. It says, well, let's divvy it up. There's $100,000 and deposit it into everybody's account, into the meal plan, so that they can spend it any way they want. So the query, right, makes a query and says, and retrieves all the students, the 1,000 students, brings them into memory, and it does a count. It does a count, and it comes up with 1,000 students. Makes sense. And so while this transaction is going on and making the decision that there's 1,000 students, and comes up with saying, well, 100,000 divided by 1,000, that's $100 each. Okay, so I need to go back and deposit $100 for everybody, right? But while this is happening, at the same time, another transaction comes in, and a new batch of students was a new batch of students enrolled in the department, and we insert 10 new students. Okay, notice that these 10 students did not make it into the count, the original count, when we came up with 1,000 students, right? It should have been 1,010, right? So now the calculation of 100,000 divided by 1,000 being 100 is wrong, right? It should have been 100,000 divided by 1,000 by 1,010. It'll be a little less than $100, right? So when we go back and deposit $100 to our students, and we update everybody's account to be, whatever amount you have plus $100, we're actually depositing $100 to 10 new students that were not in the original count. So we're going to be depositing in giving away money more than $100,000 profit that we had before. Okay, so the so the count is going to be off, right? We're going to be making money out of thin air, right? So what's going on? So we have to deal with this, right? There's tons and tons of examples of just leaving the database in an inconsistent state. We have to deal with it, right? And transactions is what's going to help us deal with this. Okay, so the way to deal with this is that we need to isolate. We need to be able to say, okay, if you are assuming that you're the only one who's reading this data, well, then let's make it so. Let's enforce that. Let's enforce the fact that if your code relies on the fact that you read those $50, right, and you have it in memory that it's 50, and you have to make 50 minus 10 equals 40, well, let's have the database enforce your logic, right? That means that if you want to enforce repeatable reads, well, then let's do that. Let's tell the database, hey, enforce repeatable reads. Meaning that if you do a read and you read $50, that record is locked. Nobody can, you don't have a parent who's going to come in and deposit $1,000. They can't do that because I'm busy, okay? Or at least they're going to be in a queue. They have to wait, right? They have to wait. Obviously, these wait times might be milliseconds, right? But at least they happen in the correct order, right? In the correct order, meaning, once I've done 50 minus 10 is 40, and I update to 40, and I release the lock, now you can come in and deposit your $1,000. It becomes 1,040. You see that? So isolation levels allow you to establish this kind of sequencing, right? So that people can wait on each other, right? And we do that with isolation levels. So each one of these issues, each one of these inconsistency risks, right? These are the inconsistency risks, right? Dirty reads, non-repeatable reads, phantom reads. These are all the bad things that could happen, right? And to solve that, right? So these are just examples of what we just saw, right? So transaction 1 reads, 20, and the other one, transaction 2, tries to update, but transaction 1 still reads it, but then transaction 2 rolls it back, right? So now transaction 1 is working with old data, right? Non-repeatable reads, right? You read something in memory, you assume that you're going to read it again, and it's going to give the same value, but it's not, right? Because transaction 2 could be coming in and changing the data, underneath you, and when you read it again, you see the same, you see a different value, right? And phantom reads, right? We're inserting data that, if you're reading several records, right, in a range, we see that, right, that if somebody could come in and insert a new record, that would have been in your original query, right? And if you read it again, you get a different set of records, right? It says, wait a minute, where do these other fields come? Where do these other records come in? They weren't there before. Well, yeah, I mean, there's other people using the database, right? So how do you deal with them? How do you deal with all these inconsistencies? And you deal with them with isolation levels, right? So isolation levels, there's 4 isolation levels that we mentioned, right? Read uncommitted, which is no isolation at all. Recommitted, repeatable reads, and serializable. Okay, so read uncommitted is free for all, right? Everybody does whatever they want. Okay, so this doesn't solve anything. You have the risk of all 3 possible inconsistencies, right? Dirty reads, non-repeatable reads, and phantom reads, right? So with recommitted, you are vulnerable to all 3 possible inconsistencies. Recommitted fixes the first one, right? The dirty reads. It fixes dirty reads, right? Repeatable reads, right, fixes both the first 2, the dirty reads and the non-repeatable reads. So it fixes those 2. And finally, serializable fixes everything, right? Fixes dirty reads, non-repeatable reads, and the phantom reads. Okay, so let's see how they do that. So read uncommitted is free for all, right? Everybody does whatever they want. There's no isolation level, and dirty reads are allowed, right? But it is the fastest, right? Because since everybody can do whatever they want, nobody's waiting on each other. It provides the fastest performance. Okay, but it also it also opens you up to potential inconsistencies. But it might be okay. You're right. There might be cases where you have tables that are read only, right? And so you don't need any this might be level is just fine. Read committed, right, guarantees that the data that you're going to read, it has been already committed, right? So this fixes the dirty read, meaning nobody will be allowed to read anything unless it has been committed, right? So it fixes this first inconsistency risk, right? And what it does is that if data hasn't yet been committed, you won't be allowed to read it. Okay, and the way it does it is by acquiring locks, right? Saying that anything that you are modifying, updating, inserting is locked, right? And only the transaction that is working on that piece of memory, right, has access to that information. Okay. Then you have repeatable reads, right? This is going to allow you to guarantee that if you're doing a select statement, right, and you get a value from that select statement, that if you do a read again, you're going to get the same exact values. And the way it does that is that it locks the record on which you apply the select statements, right? And once you're done, right, it releases those locks, right? Anybody who wants to come in and write to that record. It doesn't apply for a range of records, only individual records, right? So it fixes dirty reads and also fixes non-repeatable reads, right? But it still allows phantom reads, because phantom reads, remember, those are for ranges, right? Multiple records that might meet a criteria of if a salary is between a minimum and a maximum, right? So what fixes everything is serializable. Serializable just locks everything, right? Does a read and write lock, meaning nobody can read, nobody can write, only you. Well, you're the only transaction that has access to this, right? And it also acquires range locks, right? So that if you have a select statement where multiple records meet that criteria, they are all locked, okay? And not until you commit, right? Those locks are not released until you commit, right? And then everybody else can come in and interact with those records, right? So graphically, right, this represents on the header here, represents all the things that could go wrong, right? These are all the risks, all the inconsistency risks, dirty reads, non-repeatable reads, and phantom reads. Those are the three main risks of inconsistency. And then whereas going down here, these are all the types of isolation, right? Read uncommitted, recommitted, repeatable reads, and serializable. And this table just illustrates the things that they fix. What does read uncommitted fix? It doesn't fix anything, right? Dirty reads are unsafe, non-repeatable reads are unsafe, and phantom reads are unsafe, right? So read committed doesn't, read uncommitted doesn't fix any of these isolation, these inconsistency, right? Instead, recommitted fixes, at least recommitted fixes dirty reads, but it does not fix non-repeatable reads, and it does not fix phantom reads. And whereas repeatable reads fix both dirty reads and non-repeatable reads, but phantom reads are still allowed. And finally, serializable fixes everything, right? Now you might say, well, why don't we always use serializable? Well, because that causes the slowest performance possible, right? And whereas read uncommitted allows you to have the fastest performance, right? So again, it depends, and you have to make a choice, case by case, depending on the queries that you're making, right? Depending on what the tables are being used for, right? If it's mostly reads and whatnot, right? And so, or even considering other ways of enforcing, avoiding inconsistency, right? It could be socially acceptable, right? Where you say, hey, I'm going to be working with this table. Nobody touch it, right? And we just make we should just shake hands, right? And then say, okay, well, go ahead, go at it, work on that table. I'm not going to touch it, and that's it, right? Then we don't have to have any isolation level by the database, right? Because we are socially organizing ourselves and finding other ways of collaborating without the use of the database, right? Very much like we would work in a Google document where, hey, you work way up there in the introduction, and I'll work down here in the conclusions, and we're not trampling over each other's work, right? And as long as we avoid working in the same section, then there won't be any inconsistency, right? Very much like Git works, right? Git works somewhat like that. You're allowed to work anywhere you want at any time, and I'll just let you know if there are any inconsistency, and I'll let you resolve them, right? And so yeah, different ways of dealing with inconsistency. Okay. All right. That's all I have for you. Any questions?
Is there any chance you'll be holding any extra office hours today?
No, not today. Not today. I'm beat. When's the homework due?
It's due today.
It is due today. Okay. Well, let's see. I don't know. Let me check what my family's doing. I know there were some plans, but if they're not doing anything, I'll hold something.
All right.
Okay.
Thank you.
All right. All right, everyone. Have a great weekend.
Thank you. Have a nice weekend.
You too. Bye-bye.